In this objective, we're going to be talking about 4.9 redox reactions. So this objective states we should be able to represent a balanced redox reaction equation using half reactions. So let's first start talking about what even is a redox reaction. So it's going to involve the transfer of one or more electrons between chemical species as indicated by change in something called oxidation numbers. Of the involved species. So just real quickly, oxidation numbers is just going to be a method of tracking electrons. They aren't actually anything too specific. It's literally just to help us figure out where those electrons are being transferred. Is it from this element to this element and whatnot? We like to call them trophy numbers because they're not really technically anything serious like charges of like a polyatomic ion and all that stuff. So in redox reactions, electrons are transferred from the species that is considered the oxidized to the species that is reduced. So real quick, the oxidized species increases in oxidation numbers, and this is because they lose electrons. So here, if we're increasing in oxidation numbers, we're getting more positive, like we're losing electrons. While here, our reduced will decrease in oxidation numbers. We're getting more negative. And this is because they gain electrons. Please note that one cannot occur without the other. So one substance must gain the electron lost by another. So if you for some reason see that one lost, but you cannot find one where there's gain, you may have calculated the oxidation number wrong. Not entirely sure, but I would definitely check your work because if something's being oxidized, there will be something that's reduced. And again, we're talking about from one element on the reactant side and then looking at that element on the product side. How did it change in numbers? If you haven't noticed about me, I love mnemonics. Anything to help me memorize stuff really helps me try to make the information click. So there's two different little sayings that you can use to memorize oxidation and reduction. The first one is called oil rig. So the O in oil stands for oxidation. I stands for is, L is loss, and this is loss of electrons. And the other is rig. This stands for reduction, is gain of electrons. Oil rig is what I learned in college. You can definitely use the other one I'm going to show you, but oil rig is the more commonly used mnemonic to memorize that oxidation is loss and reduction is gain. The other one is called Leo the lion goes grr. Okay, this one is a bit harder to understand. In Leo, it means loss of electrons, oxidation. So here, that's loss electrons, oxidation, while the grr part means gain of electrons, reduction. Sorry, my pen is being a little wonky. So here, Leo the lion goes grr. Again, use whatever you would like. Oil rig tends to be the fan favorite, but Leo the lion goes grr definitely works as well. So let's talk about those oxidation numbers. Oxidation numbers, or we can call them states, are assigned to each of the atoms in the reactants and products just to help us figure out what is our oxidized and what is our reduced. Generally, the charge of that said element tends to be kind of what the oxidation number will be, but let me just show you a few things. So I'm going to look at these three down here first before I start showing you the chart. Let me zoom in. The sum of all the oxidation numbers in a compound must equal the charge of the compound. So if we're working with a neutral compound, like a salt, the overall oxidation number should equal 0 because it's neutral. Charges are written with the number first, then the sign of the charge. So what that means is, if I look at sodium, the ion, 1 positive, that is the charge. If you wanted to write oxidation number, it's positive 1. So if you were ever wondering why for monatomic or polyatomic ions, we always wrote the number, then the symbol, this is the reason why. Next, oxidation states are written. Oh, I already said that. Yep, so charges are written number then symbol. Oxidation states are written symbol then charge. This has a lot of rules. The ones that tend to be the easiest to memorize are these right here. So neutral substances. So if you see an element by itself, just in its neutral form, this could be a diatomic element as well. 0 is going to be the oxidation number. Monatomic ions. If you just see calcium 2 positive, its oxidation number will be positive 2. Okay. Group 1 and group 2 elements are alkaline earth metals. If it's going to be in a compound, it will be whatever charge it is as an ion, unless it is a metal by itself. So this kind of goes with those first two I was talking about up here. That's why I said they're fairly easy. Hydrogen tends to be fairly easy as well. It can be +1, 0, or -1. That's because if we talk about hydrogen by itself, 0. If you see hydrogen listed first in ionic compound, +1. But please note we do have hydrides. So looking at this example of sodium hydride, sodium's +1, so hydride has to be -1. Your issue groups are going to be these. Oxygen. Oxygen can be 0, -1, -2, or a half. I have examples all right here. And then our halogens or even our nonmetals can cause a lot of issues. And I feel like I just have to show you examples, but please know that polyatomics are going to cause our biggest issues. So let's look at these examples right here. So what we're going to do is we're going to assign oxidation numbers to every single element in these two reactions. So if I see Na solid, this is neutral substance by itself, oxidation number 0. Then I look at chlorine. Chlorine's a diatomic element, just chilling by itself, 0. Then I have NaCl. So here I need to think about ions. Sodium will be +1 because its monatomic ion charge is 1-. Chlorine will be -1 because it would have a 1- charge as the ion. And if you look, NaCl, we don't have to do this part, but it will equal 0 because it's a neutral compound. So Na goes from 0 to +1, and chlorine goes from 0 to -1. So now you have to decide, did those numbers change? They sure did. Now we have to decide which ones are oxidized and which ones are reduced. So remember oil rig, so oxidation's loss, reduction is gain. So I can see that the sodium is gaining more positive. So this will be my oxidized. Then my Cl goes from 0 to -1. It is getting more negative. Here it's gaining electrons. This will be my reduced. Going to the next one. Here, lead. Now, when we get to transition metals, it may be a little bit harder to tell because transition metals can be multivalent. Here I see the oxygen. The oxygen will be -2 because it's just in a compound. Here, this means that lead has to be +2 because the sum of those numbers will equal 0, the neutral charge of the lead-2 oxide. Hydrogen by itself will be 0. Then I see lead as a product by itself. This will be 0. Then I have water. So water will be +1 for the hydrogen and -2 for the oxygen. And I knew that because hydrogen is listed first, it wouldn't be a hydride -1. Anyways, if I wanted to take the sum of all those numbers, we would have 2 hydrogens making that 0. Next, let's look at all 3 of those elements and see how they changed. So lead went from +2 to 0, oxygen went from -2 to -2, and hydrogen went from 0 to +1. So here, my lead ends up being my reduced. It's getting more negative, it gained electrons. Nothing happened to my oxygen because it stayed the same oxidation numbers. Then for hydrogen, this would be oxidized because it is getting more positive, and that will call it good for those two examples. Now let's move on to the problem I do, and I'll do these two examples with you. So we're going to look at these two examples and see which of the following are considered actually redox reactions. If it is a redox reaction, we will identify which atom is being oxidized, which atom is being reduced. If it's not a redox reaction, we're going to be seeing that each of the elements on either side are going to stay exactly the same. All right, let's look at the first example. So I see zinc by itself. This is going to be 0. Next, I see CuCl. Well, I know that chloride, the ion, is 1-, so this has to be -1. And so since I see 1 copper by itself, it's safe to assume that it's +1. Next, copper as a product will be 0. And then for the zinc chloride, I know chloride's -1 again, but the zinc is going to be +2 because there's 2 chlorides there in the formula. So writing out each element that I see in this reaction, I see that zinc goes from 0 to +2, copper goes from +1 to 0, and chloride goes -1 to -1. So here to figure out what's being oxidized, we're going to look at the one that's going to be becoming the more positive, losing electrons. That's going to be zinc. While the copper is going to be starting to get more negative. Call this reduced. And then here the chloride stayed the same. So yes, this is a redox. All right, next example, I have calcium carbonate. So here, calcium as an ion in the ionic compound would be 2 positive. So here would be +2. And I know all my oxygens generally will be -2. We're going to need to figure out what carbon is. So to do this, we said that the sum of all the oxidation numbers would equal the charge of the compound or the species, whatever it is. Here, this should be a neutral compound. So here, calcium is going to be +2, and there's only one of them. Carbon, I'm solving for carbon, and there's only one of them. And then for oxygen, it's -2, and there's 3 of them. 3 of them because of that subscript. So here, all of it should equal 0. So here I have 2 plus x minus 6 equals 0. X minus 4 equals 0. Bring that to the other side, I get +4. So here, x will be +4, and I'll trade places up there. +4. Okay, next looking at the other examples, the products here, calcium is +2, oxide's -2, and then here oxygen's -2, and essentially that carbon's going to be +4 again, and that's because I have x minus 2 times 2 equals 0, again because of that subscript and the oxidation number for oxygen's -2, I still get +4. So right now, looking at calcium, carbon, and oxygen, calcium goes +2 to +2, carbon goes +4 to +4, oxygen goes -2 to -2. So here, this is not a redox because none of the elements have changed oxidation numbers from the reactant side to the product side. Well, I have problem 2 for you, and it has 2 chemical reactions. You're going to look for the oxidation numbers for both and then decide if it's a redox reaction or not. So why don't you pause the video, try this out yourself, and then click play, and I'll go over the answers. So in the first example, you can see that the magnesium went from 0 to +2. That's considered oxidized. And the hydrogen went from +1 to 0. That would be our reduced. So this is a redox reaction. And then in the other example, you will see that everything ended up staying the same on either side. This would be an example of not a redox. If you actually look, this would be considered an acid-base reaction, which we'll talk about in the next objective 4.7 and 4.8. Here, seeing a double replacement is probably a big indication that it's not going to be a redox reaction. So most of our other chemical reactions, synthesis, decomposition, single replacement combustion, those are going to be redox reactions, most cases. All right, we're going to talk about half reactions and then we're done with the video. So half reactions, we can actually balance the redox reactions that occur in aqueous solutions. So in this procedure, we actually break down the overall equation into two single half reactions, one for the oxidation half reaction, and the other one for the reduction half reaction. If we add both of those together, those will get us our overall balanced equation. So real quick, when we talked about oxidation, it's losing electrons. So since it's losing electrons, I want you to think as losing as a product. If we talk about our reactants on the left, products on the right. So here, oxidation, if it's losing, it's breaking apart. It would be decomposing in a sense. So here we would see our electrons being lost as a product. And then for reduction, since we're gain it as a reactant. Okay, so what that would look like is this. If I had element X and it broke up to positive, okay, so here it's getting more positive, it lost an electron, we would show the electron as a product. And then for reduction, let's say we had element Y became element Y negative, it got more negative. Here we would show the electron as a reactant because it gained it to make its new product. Okay, this is going to be our general format that we will use for half reactions. And then this was going to be nice. We can balance the half reactions, like I said, and add them together. And this will actually cancel out electrons on either side. You just need to make sure that those electrons are balanced. So if this had a 2 right here, we would need to multiply the other one all by 2 to get those 2 electrons. But yeah, just making sure that the mass and number in each type of atom are staying the same to help with that charge. All right, so just a few things for balancing half reaction steps. First, you're going to write down unbalanced oxidation half reaction. You're going to balance the number of atoms on both sides. You then, once the atoms are balanced, you're going to check charge. So that is when we're going to make sure we add electrons to balance charge. So if your element went from 0 to positive 2, you would show a change of 2 electrons. You would repeat steps 1 through 3 for a reduction half reaction. So kind of like I was showing you on the previous page. Then you're going to compare number of electrons in each half reaction. Make sure that they're the same so they can cross off. If they're not, make sure you fix it. Then you're going to combine both reactions to get overall. Here, electrons will cancel out. And then finally, just do a final check to make sure equation is balanced. So I'm going to do the first example with you, and then I'll give you the second one for you to try on your own. So here, consider the following. Here, first things I would do is I would figure out what the oxidation numbers are. So since these are all monatomic ions, the charge of the ion will be the oxidation number. So we have +3, +2, +2, +4. So based off step 1, let's make our oxidation half reaction. So remember, oil rig, so we have to figure out which species is losing electrons. That's going to be the tin. So tin goes from 2 positive to 4 positive. Then let's see what the change of electrons are, and we're going to add those electrons to the reaction. So tin went from 2 to 4. That's a change of 2 electrons. You see, I put it as a product because it's losing electrons, it's exiting. Next, we need to make our reduction half reaction. Here we have Fe going from 3 positive to 2 positive. That is a change of 1 electron. So I'm going to put 1 electron as the reactant. Now to follow our next step, we need to make sure our electrons are the same. Here, they right now do not match, so I'm going to multiply the entire reduction by 2 to make that 2 electrons. Now I can add both my oxidation and reduction together. I'm going to bring this one down here so you can see it a little bit better. So to add these together, my 2 electrons will cancel on either side. And my overall will be 2 Fe3 positive, 10 2 positive, 10 4 positive, and 2, oh, sorry, I forgot to put that 2 right there, 2 Fe2 positive. This would be our balanced overall equation. All right. So why don't you pause the video and try this one out yourself, and then when you're ready, click play and I'll go over the answers. So I wrote out my oxidation and reduction half reaction. I saw that the aluminum changed by 3 electrons and the zinc changed by 2. So here, found a common factor of 6. So here I multiplied aluminum all by 2 and then the zinc all by 3. And then you'll see my now 2 new half reactions. I now can cancel them out. We'll add them together and cancel out the 6 electrons to get my overall. I'll have coefficients of 3 in front of all the zincs and then 2s in front of all the aluminums. And now my overall balanced redox reaction for the reaction between zinc and aluminum.